It's Sleepy Steve, helping you to fall asleep and study. Remember to subscribe to help Steve-O out, and I will keep making more sleepy stories. Tonight, we are stepping quietly into Unit 3 Physics, where the motion of objects becomes a little more detailed, a little more mathematical, and a little more powerful. The room is calm, the pencil is sharp, the page is open, and the first idea waiting for us is that forces do not always act neatly in one straight line. Before we begin, let your shoulders soften, let your breathing slow down, and imagine that you are sitting beside a wide, still sports oval after sunset. The lines on the grass are faint, the air is cool, and somewhere on the field there is a ball, a trolley, or a small object ready to be described not just by words, but by arrows, directions, and careful thinking. In Unit 1 and Unit 2, we built the foundations of motion. We learned that displacement, velocity, and acceleration are vector quantities because they have both size and direction. We learned that force can change the motion of an object. We learned that Newton's laws explain how objects respond when forces act on them. Now, in Unit 3, we begin to use those ideas with more precision, because real objects are often acted on by several forces at the same time, and those forces may point in different directions. The central question for this episode is gentle but important. How can we use Newton's laws when forces act in two dimensions? The answer begins with a model. In physics, we often simplify a real situation by drawing only the features that matter. We replace the object with a point, we draw the forces as arrows, and we choose directions so that the situation becomes clear enough to analyze. This is where a free body diagram becomes one of the most useful tools in physics. A free body diagram is a simple diagram showing the forces acting on a single object. It does not show every object in the whole scene. It does not show the background or the surface in detail. It shows the object of interest and the forces acting directly on that object. That simple choice is what makes the diagram powerful. In an exam, if you are asked to analyze forces, Sleepy Steve wants you to pause and ask, what is the object? What forces act on it? What directions do those forces act in? Are any forces balanced? Is there a net force? Is the object accelerating? These questions are quiet, but they are also the backbone of the answer. The forces you meet most often include weight, normal reaction force, friction, tension, thrust, drag, and applied force. Weight is the gravitational force acting on an object, and near Earth's surface, it acts vertically downward. The normal reaction force is the contact force from a surface, acting perpendicular to that surface. Friction acts parallel to a surface and opposes the motion or the tendency of motion. Tension acts along a string, rope, or cable. Thrust or applied force may push or pull in a chosen direction. Drag or air resistance opposes motion through a fluid such as air or water. The first exam trap is to mix up mass and weight. Mass is the amount of matter in an object measured in kilograms. Weight is a force measured in newtons. Weight depends on gravitational field strength. So, if a question gives the mass of a person, a crate, or a car, you may need to calculate the weight before you draw or analyze the vertical forces. The second exam trap is to draw forces that do not actually act on the object. For example, if a ball is flying through the air after it has left someone's foot, there is no longer a kicking force acting on it. Once contact has ended, that force is gone. The main forces are usually weight downward and, if air resistance is considered, drag opposite the motion. The ball keeps moving because of its inertia, not because a forward force continues to push it through the air. Newton's first law says that an object will remain at rest or continue moving at constant velocity unless acted on by a net external force. This means that if the net force on an object is zero, the object does not have to be stationary. It could be stationary, but it could also be moving at constant velocity. Constant velocity means no change in speed and no change in direction, so the acceleration is zero. Newton's second law links net force, mass, and acceleration. In words, the acceleration of an object is in the direction of the net force, is directly proportional to the net force, and is inversely proportional to the mass. The familiar equation F net equals ma is not just a calculation tool. It is also a statement about cause and effect. A net force causes acceleration. If the net force is larger, the acceleration is larger. If the mass is larger, the same net force produces a smaller acceleration. Newton's third law says that when two objects interact, they exert equal and opposite forces on each other. These forces are equal in magnitude, opposite in direction, and act on different objects. That last part matters. Because the two forces act on different objects, they do not cancel each other out on a single free body diagram. If you are drawing the forces on one object, you only draw the forces acting on that object. Now let us move softly into 2 dimensions. Imagine a sled being pulled across level ground by a rope. The rope is not horizontal, it is angled upward. The tension in the rope has 2 effects at once. Part of the tension pulls the sled forward, and part of the tension pulls the sled upward. The sled does not simply respond to the full tension as if it were horizontal. Instead, we resolve the tension into horizontal and vertical components. Resolving a vector means splitting it into perpendicular components. Usually we split a force into a horizontal component and a vertical component. The components are not extra forces. They are a mathematical way of representing the original force. The original angled force and its 2 components are equivalent, meaning the components together have the same effect as the original force. For an angled force, the horizontal component is commonly found using cosine, and the vertical component is commonly found using sine, depending on how the angle is measured. If the angle is measured from the horizontal component is f cosine theta, and the vertical component is f sine theta. If the angle is measured from the vertical, the roles may swap. So do not just memorize a pattern. Look carefully at where the angle is placed. A calm exam method is to draw the triangle. Put the original force as the hypotenuse, then draw the horizontal and vertical components. Label the angle. Then ask which component is adjacent to the angle and which is opposite. Cosine links the adjacent side to the hypotenuse. Sine links the opposite side to the hypotenuse. This little pause can prevent many mistakes. Once the forces have been resolved, we analyze each direction separately. Horizontal forces affect horizontal acceleration. Vertical forces affect vertical acceleration. On level ground, many objects do not accelerate vertically because the upward and downward forces balance, but the same object may accelerate horizontally if the forward forces and backward forces do not balance. Let us return to the sled. Vertically, weight acts downward. The normal reaction force acts upward. The upward component of tension also acts upward. If the sled stays on the ground and does not lift off, vertical acceleration is zero, so the upward forces must balance the downward weight. This means the normal force may be smaller than the weight, because the rope is helping to support some of the sled's weight. Horizontally, the forward component of tension pulls the sled forward. Friction may act backward. If the forward component is larger than friction, there is a net force forward, and the sled accelerates forward. If the forward component equals friction, the horizontal net force is zero, and the sled either stays at rest or moves with constant velocity. In an exam, a strong answer does not simply say, the object moves because force is bigger. A strong answer says that the horizontal component of the applied force is greater than the opposing frictional force, so there is a non-zero net force in the forward direction. By Newton's second law, this net force causes the object to accelerate in the direction of the net force. That is the kind of calm, precise chain of reasoning VCE style questions often reward. Inclined planes are another important two-dimensional situation. Imagine a crate resting on a ramp. Weight acts vertically downward, not straight down the ramp. The normal reaction force acts perpendicular to the surface of the ramp. Friction acts parallel to the surface of the ramp, opposing motion or the tendency to slide. Because the surface is tilted, it is usually helpful to choose axes that are parallel and perpendicular to the ramp rather than horizontal and vertical. This is an important modeling choice. In physics, axes are tools. You do not always have to choose horizontal and vertical axes. If the object is on a slope, choosing one axis along the slope and one axis perpendicular to the slope often makes the problem simpler. The acceleration is usually along the slope, and there is usually no acceleration perpendicular to the slope because the object does not fly off the surface or sink into it. For a crate on a slope, weight can be resolved into two components. One component acts parallel to the slope and tends to pull the crate down the slope. The other component acts perpendicular to the slope and presses the crate into the surface. The normal reaction force balances the perpendicular component of weight if there is no acceleration perpendicular to the slope. Students often make the mistake of saying that the normal reaction force equals weight on an incline. On a horizontal surface with no other vertical forces, that may be true. But on an incline, the normal reaction force is less than the full weight because it balances only the component of weight perpendicular to the slope. The component of weight parallel to the slope is what tends to make the object slide. If friction is absent, the net force down the slope is the component of weight parallel to the slope, and the object accelerates down the slope. If friction is present, friction acts up the slope when the object slides or tends to slide downward. The net force down the slope is then the downslope component of weight minus friction. Once again, Newton's second law connects that net force to acceleration. The words balanced and unbalanced need careful use. Forces are balanced when the vector sum of forces is zero. That means there is no net force and no acceleration. Forces are unbalanced when the vector sum is not zero. That means there is a net force and the object accelerates in the direction of that net force. In two dimensions, a force can be balanced in one direction and unbalanced in another direction. A car may have balanced vertical forces but unbalanced horizontal forces. A crate on a ramp may have balanced perpendicular forces but unbalanced parallel forces. Let us think about a car driving around a curve, because this helps us see that acceleration is not only about speeding up or slowing down. If a car changes direction, it is accelerating, even if its speed stays constant. There must be a net force toward the center of the curve. That force might come from friction between the tires and the road, or from a combination of forces on a banked track. The direction of acceleration is toward the center because the velocity direction is changing. This idea is the beginning of circular motion, which comes in the next episode. For now, the key Unit 3 message is that Newton's second law is a vector relationship. The net force and acceleration point in the same direction. If the acceleration is sideways, the net force must be sideways. If the acceleration is down the slope, the net force must be down the slope. If acceleration is zero, the net force must be zero. When solving problems, it helps to move through a calm sequence. First, identify the object. Second, draw a free body diagram. Third, choose axes that make the problem simple. Fourth, resolve any angled forces into components. Fifth, write separate net force equations for each direction. Sixth, substitute values carefully. Seventh, interpret the answer in words, including direction. Notice that this method is not rushed. It is like walking slowly along stepping stones across a pond. Each step supports the next. If you skip the diagram, you may lose the direction of a force. If you skip the axes, you may resolve forces the wrong way. If you skip the words, you may calculate a number but fail to explain the physics. The calm method is the strong method. Let us practice the language without needing a heavy calculation. Suppose an object is pulled by an angled force across a rough horizontal surface. An exam explanation might say, the applied force has a horizontal component that acts in the direction of motion and a vertical component that reduces the normal reaction force. Because friction depends on the normal reaction force, the upward component may reduce the frictional force. If the forward component of the applied force is greater than friction, the object experiences a net force forward and accelerates forward according to Newton's second law. That answer is powerful because it connects the diagram to the forces and the forces to the motion. It does not simply list terms, it explains relationships. In Unit 3 Physics, the word because is often your friend. The object accelerates because there is a net force. The normal force is smaller because part of the applied force acts upward. Friction changes because the normal force changes. The direction of acceleration is the direction of the net force. Another useful phrase is vector sum. The net force is the vector sum of all forces acting on the object. Vector sum means direction matters. A 10 Newton force east and a 10 Newton force west cancel. A 10 Newton force east and a 10 Newton force north do not simply become zero. They combine to make a resultant force at an angle. This is why diagrams matter so much in two-dimensional problems. The resultant force is another name for the net force. It is the single force that would have the same effect as all the forces combined. If several forces act on an object, you can replace them mathematically with one resultant force. The object accelerates in the direction of that resultant force. This is the quiet heart of Newton's second law in two dimensions. Now think about equilibrium. An object is in translational equilibrium when the net force is zero. It may be resting on a table, hanging from two cables, or moving at constant velocity. In two-dimensional equilibrium problems, the sum of forces in the horizontal direction is 0, and the sum of forces in the vertical direction is 0. If a sign is hanging from two angled cables, each cable tension can be resolved into components, and the horizontal components may balance each other while the vertical components support the weight. This is where Newton's first law and Newton's second law meet. If acceleration is 0, net force is 0. If net force is 0, acceleration is 0. Equilibrium does not mean no forces are present. It means the forces present add to 0 as vectors. A book on a table has weight downward and normal force upward. A hanging sign may have weight downward and two tensions upward and sideways. Many forces can act, but the vector sum can still be 0. For VCE physics, you should also be careful with sign conventions. If you choose right as positive, then forces to the right are positive and forces to the left are negative. If you choose up the slope as positive, then forces up the slope are positive and forces down the slope are negative. A negative acceleration does not mean the object is doing something wrong. It simply means the acceleration is in the direction opposite to your chosen positive direction. Units are part of the language too. Force is measured in newtons, mass is measured in kilograms, acceleration is measured in meters per second squared, angles are measured in degrees unless otherwise stated. Components of force are still forces, so they are still measured in newtons. A neat answer includes both magnitude and direction, because a force or acceleration without direction is incomplete when direction matters. As the night becomes quieter, let us gather the main ideas. A free body diagram shows the forces acting on one object. Newton's laws connect force and motion. Angled forces can be resolved into perpendicular components. Forces can be analyzed separately in each direction. If the vector sum of forces is 0, acceleration is 0. If the vector sum is not 0, the object accelerates in the direction of the net force. For exam responses, remember the gentle chain. Identify forces, resolve components, find net force, apply Newton's second law, and explain the motion. Do not rush past the diagram. Do not treat components as extra forces. Do not assume normal force always equals weight. Do not forget that acceleration has direction. And do not forget that a constant velocity means 0 acceleration, even when the object is moving. Now, as you let this episode settle, imagine the arrows on the page becoming still. The downward arrow of weight, the upward arrow of the normal force, the angled arrow of tension, the small backward arrow of friction, all resting quietly in balance or leaning gently toward motion. Physics is not trying to make the world noisier tonight. It is simply giving you a calmer way to see the hidden structure of movement. Sleepy Steve wishes you a great sleep. Don't study too hard. Subscribe for more sleepy stories.